All right, we're about to jump into a topic that honestly feels like it's been pulled straight out of science fiction. We're talking about quantum computing. This is a whole new kind of machine that plays by the bizarre, mind-bending rules of quantum mechanics to solve problems that our best supercomputers today couldn't crack in a billion years. So here's how we're going to tackle this. First, we'll look at the fundamental building block, a new kind of bit. Then, we'll dive into the weird physics that makes it all possible. After that, we'll see just how hard it is to build one of these machines, find out what they're actually good for, and finally, take a look at the global race to make it all happen. Okay, let's get right to it. To even begin to understand a quantum computer, you have to throw out your idea of the most basic piece of information, the bit. This really gets to the absolute core of it all. Every device you own, from your smartphone to your car, runs on classical bits. Just think of them as simple light switches. They're either off, which is a 0, or they're on, which is a 1. End of story. But a quantum bit, or what we call a qubit, well, that's a whole different beast. It can be a 0, it can be a 1, or, and this is the mind-bending part, it can be both at the exact same time. And this right here is the secret sauce. This is where the exponential power comes from, because a single qubit can hold multiple values. When you start linking them together, the number of possibilities just explodes. 2 qubits can hold 4 states at once, 3 qubits can hold 8. Get up to just 300 qubits, and you can represent more states simultaneously than there are atoms in the known universe. Just try to wrap your head around that. It's like having a computer that can run an almost infinite number of calculations all at the same time.
So you're probably asking, how on earth is that even possible? Well, to understand how a qubit can be in this both states at once situation, we have to embrace a couple of core ideas from quantum mechanics that are, let's be honest, just really, really weird.
First up is this idea called superposition. This is the magic property that lets a qubit exist as a blend of both 0 and 1. It's not one or the other, it's a fluid, probabilistic mix of every possibility all at once. A great way to think about this is to picture a spinning coin. While it's spinning in the air, is it heads or tails? Well, it's neither. It's in a superposition of both. It's only when you slap it on the table, when you measure it, that it's forced to choose and becomes either heads or tails. That's exactly what a qubit does. Okay, so if you thought that was strange, get ready for entanglement. This is where quantum mechanics starts to feel like telepathy. You can take 2 qubits and link them together so that they behave as a single system, no matter what. And here's the spooky part. If you measure one of those entangled qubits and it collapses to a 0, you instantly know with 100% certainty that its partner is also a 0. It doesn't matter if that other qubit is in the next room or in a galaxy a million light years away. The connection is instant. Einstein famously called this spooky action at a distance because it seems to break the laws of physics, but it's real. Of course, there's always a catch, and this one is a doozy. The second you try to look at a qubit to see what state it's in, the moment you measure it, the whole quantum party is over. The superposition collapses. That beautiful blend of possibilities shatters, and you're left with a boring old classical 0 or 1. All that incredible quantum information vanishes in an instant. So we've got the mind-bending theory down, but how in the world do you actually build a machine that can control something so delicate and fragile? Well, it turns out it's one of the biggest engineering challenges of our time. You see, every quantum computer has a mortal enemy, something called decoherence. A qubit's quantum state is unbelievably fragile. The universe is basically trying to mess with it constantly. The slightest vibration, a tiny fluctuation in temperature, a stray magnetic field, any of it can cause the qubit to decohere, destroying its quantum state and creating errors. So to fight this, engineers are trying a bunch of different things. And it's all about trade-offs. You've got superconducting circuits, like the ones Google and IBM use. They're incredibly fast, but you have to keep them chilled to temperatures colder than deep space. Then there are trapped ions, which are way more stable and accurate, but they're also a lot slower. And some are even trying to use particles of light, which can work at room temperature, but getting them to actually talk to each other is a massive hurdle. And to really give you a sense of the scale of this problem, look at this. The absolute best systems we have today achieve about 99.5% accuracy on a basic operation. Now that sounds great, right? An A+. But imagine you need to run a calculation with 1 billion steps. With that error rate, things go wrong so fast that your final answer is complete garbage. It's like trying to build a skyscraper where 1 out of every 200 bricks is faulty. Okay, so you're probably thinking, this sounds ridiculously hard. Why even bother? Well, the reason we bother is because for a very specific set of problems, the payoff isn't just a little bit better, it's world-changing. Let's start with the big one, the one that keeps security agencies up at night, Shor's algorithm. Now, what it does sounds kind of boring. It finds the prime factors of huge numbers. But here's the deal. Almost all modern encryption, the stuff that protects your bank account, your private messages, everything, it's based on the fact that this is an impossibly hard problem for normal computers. For a quantum computer running Shor's algorithm, it's easy. It could crack our modern security wide open. Then there's something called Grover's algorithm. Think of it as the ultimate search tool. Imagine you're looking for a single piece of information in a massive, totally disorganized database. A regular computer has to look at every single entry one by one, but Grover's algorithm can use superposition to check them all in a much smarter way, giving it a huge speed up. A search that would have taken a classical computer an entire year could be done in just a couple of weeks. This is a game changer for drug discovery, logistics, and all sorts of optimization problems. So with this kind of incredible power on the table, you can bet there's a race going on, a massive global race between companies and countries, all scrambling to be the first to build a truly useful, error-corrected quantum computer. And you've got all the heavy hitters in this race. IBM and Google are leading the pack with their superconducting approach. But then you have companies like IonQ and Quantitinium who are betting that their more stable trapped ion technology will win in the long run. Microsoft is even playing a different game entirely, working on a very theoretical type of qubit they hope will be naturally immune to errors. Everyone is placing their bets. But here's what might be the most amazing part of all. This isn't just happening behind closed doors and secret labs anymore. Right now, today, you can go online through platforms from Amazon, Microsoft, and IBM and actually run code on a real quantum computer. This future is literally at our fingertips. So let's be totally clear. A quantum computer is never going to replace your laptop for checking email or watching videos. They're specialized tools for specialized problems. Think of it less like a new smartphone and more like the Hubble Space Telescope. You don't use it for everyday tasks, but the discoveries it makes can change our understanding of the universe. By solving these impossible problems in medicine, materials, and finance, quantum computers have the potential to change almost everything else about our world. We are standing at the very beginning of a new age of computing. The quantum leap is just getting started.